Okay, good morning. We're going to get started now, and maybe we'll even finish up this chapter on chemistry today. That's sort of my goal. A couple of comments. The lab test 1. You probably saw it on my email from last night regarding the lockdown browser. When the lab test was initially set up, the lockdown browser was supposed to be in place with it, and it wasn't until this weekend that I discovered that the lockdown browser was not activated like it was supposed to be. And a number of you had already taken your lab test. The decision to go ahead and delete all the exams, other than people that have, and a number of people have taken it with a lockdown browser now. But 5 or 6 people had taken it without the lockdown browser in place. To avoid any appearance of having an advantage by not having the lockdown browser in place, I had to delete all the exams so that people could take them over again. I will say that for a lot of people, it gives you a second chance to do better on a lab exam than you had done initially. If you come out doing less than you did the first time, well, that's just the nature of the exam, and I apologize for that, but that's just how it's going to break out. I am bound by the syllabus to make sure everybody gets a fair exam, and I don't want even the appearance that someone could take the time without the lockdown browser to flip through notes and look up answers. Another thing to state is that you should never, ever be using your notes in these exams. This is a note-free exam. There's nothing, if you were taking this in the classroom, you would have nothing in there with you except the test and a pencil, and that's it. No resources, nothing else. Even if it was, even the lab exam, you would only have a pencil to mark the answer down with. So it's unfortunate. I wish I'd caught it sooner. I made the assumption that since that the lockdown browser was going to be installed automatically, that it would actually do that. So I had to go back in and reinstall it. So I am sorry for any confusion over that. I did extend the deadline on the lab test so that I extended it to the 21st, I think, which is next Tuesday. So you have more time. Again, as I've told a number of people, if you didn't do as well in the first lab test that you took as well as you would like, you have an opportunity to improve that score now. But I will also remind you that the lab grade is not a grade of real concern for getting into any healthcare program. The only grade that's reviewed and evaluated is the lecture grade. So lab grade only can help your GPA a little bit because it's only 1 credit hour. But it's the lecture grade that gets you points that add up into admission into any of the programs. So try not to stress over that lab grade or that lab test. There's 3 other lab tests coming. Most people that do okay on the first test tend to do really well on the next ones after this. So anyway, any comments or questions on anything?
Did you extend the time also, or is it still just 1 hour to take the exam?
Yep, I can't. Okay. I just realized I had my sound down. Did anybody hear what I just said?
Yes.
Okay, good. Thank you. I thought that would be so typical, to spend 5 minutes talking about a topic area or an issue and then realize that, oh, the sound's down. Nobody can hear me. So anyway, Jasmine, if you made a comment, I didn't hear you, and I apologize.
No, I was asking if it was still just the 1 hour because I got confused if you extended the time or the deadline for the.
Well, it's still, the test is still an hour, but I extended the deadline to the 21st of September. So I kicked it back about almost a week more because a lot of people that took it early may have to review the material again to take it. So I wanted to give, I'm trying to be as absolutely fair as I can to everybody. So.
Okay, thank you.
Welcome. Okay. Okay, having said all that, let's go ahead and get into the content for today. We're going to pick up on, open this up and go into lipids. And shrink this. And okay, so lipids, the second of the large organic molecules that we deal with in biochemistry. Carbohydrates were the first. Carbohydrates are sugars and starches. They're all based off of glucose molecules. And glucose is the molecule we use for fuel in our bodies. We break starches down to glucose. We break carbohydrates, large chains of carbohydrates like glycogen and starch down to glucose. It's interesting that the calorie content in a gram of carbohydrates is only 4 calories, but a gram of lipid, a fat, if you will, is 10 calories. There's a lot more fuel available in a gram of lipid, a gram of fat, than there is in a gram of carbohydrates. I think I may have made this point on Monday, that if you have like you get a fruit bar or a cereal bar, or you get an apple or something, or if you look up the calorie makeup of an apple, you'll see that all the calories in an apple come from the carbohydrates, the starches, whereas a cereal bar, like a Nutrigrain bar or something, it has both carbohydrates and fats in it. And the calories from the carbohydrates, if it has 4 grams of carbs, it's going to be 40 calories. If it has 10 grams of fat, it's going to be 100 calories in there. So that you combine the two to get your total total calorie content in the cereal bar. There are more calories available in fats than there are carbohydrates. The calories are the source of energy. And the beauty of the way our body works is we can take those fats and break them down into glucose when we need to. So it isn't that we're using the wrong material, because we're using glucose as the source. We use glucose as our source of energy. And if we get that glucose from carbohydrates, that's a simple approach. If we get it from fats, we have to break the fats down and form glucose from the fats, which we do. And we use it for the source of energy. So anyway, now there are 4 types of lipids that we deal with in human physiology. The triglycerides, which are the neutral fats, they have no charge. The triglycerides, if you've ever had blood work done, you know that they look at your triglycerides in your blood, for example. These are the fats also that we consume. These are the things that show up in butter and in oils, cooking oils, that show up in lard or shortening. These are the fats that we encounter all the time. This is what if you eat something and on the label it says 130 calories, 80 calories from fat, 20 calories from sugars or whatever. That's what we're talking about. So this is, we encounter this all the time. These triglycerides are in healthcare, are the fat that's in our blood and the fat that's stored in our tissues. We also have the phospholipids. Phospholipids make up the cell membrane structure of all of our cells. Our cells have a cell membrane is double layered. Now, we remember when we looked at the cells, the cheek cell slides, and you could see the edge of the cell. You couldn't see the membrane, but you could see where it was located because you could see the edge of the cell. The edge of the cell is where the membrane is located. The membrane is a double layer of what we call phospholipids. Remember, lipids are similar to the carbs in the sense that they're made of carbon and hydrogen and oxygen, but not in the same ratio of 1 to 2 to 1 that we see in the carbohydrates. We also see in some cases phosphate thrown into the mix. That's what happens in the phospholipids. The cell membranes are made up of a double layer of phospholipids. This is the only place where we encounter most of those fats with a phosphate attached to it. The steroids are the third category. Steroids are based off of cholesterol. Cholesterol is a four-ringed structure that is the basis of all the steroid hormones, including estrogen and testosterone. It is the basis of all of the adrenal hormones, the adrenal cortex, like aldosterone, which helps to regulate our blood pressure, and cortisol, which regulates our glucose balance in our bodies. So the steroids are all based off cholesterol. Cholesterol itself is involved in creating a support structure for cell membranes. We'll say right now that cholesterol is not evil, even though cholesterol gets a lot of bad implications in healthcare. Cholesterol itself is not evil. In fact, cholesterol is necessary in our bodies. And the last one are the Accosinoids. The Accosinoids are they're sometimes considered in their own little category. They're part hormone, or actually maybe they are. The endocrine system doesn't want them because they're not true hormones, even though they are. And the fats don't really want them because fats say that they're hormones. But what they do is when we have a cut or a scratch, and we have a red area around that cut or a scratch. That red area is actually the sign of that our system is working. It's what we call inflammation, or the inflammatory response. And the inflammatory response causes more blood to come to an area where there's an injury. That's why it's red. That's why it's warm. When we bring in more blood, we bring in more red cells, we bring in more white cells to fight infection, we bring in more oxygen, we bring in more glucose to promote healing and take away debris and dead cells and dead bacteria and carbon dioxide and other waste. So it's a good thing. And the Accosinoids release a type of molecule called prostaglandin, which mitigates the inflammatory response. So it's a type of hormone. We'll talk about it again in AP2 when we get to the endocrine system. But again, the endocrinologists argue that the Accosinoids aren't hormones, and the people that deal with lipid chemistry say, well, the Accosinoids aren't lipids either. So we go back and forth. Okay, so what about the triglycerides? If you've ever had blood work, you always see somewhere in the list of the blood work is your triglyceride level. Now, the triglycerides make up the fats that we deal with. If the triglyceride is solid, it's a fat. If the triglyceride is an oil, it's a liquid. So we have solid fats and we have liquid fats. They're oils when they're liquid, and they are fats when they're solid. Butter is a solid fat. So we call it, it's a fat. Butter is a fat because it's solid at room temperature. Olive oil is liquid at room temperature, so we call it an oil. Gee, imagine that. Olive oil is called an oil. But the basis is that what do these molecules look like? What do these triglycerides look like at room temperature? If it's a solid at room temperature, it's a fat. If it's a liquid at room temperature, it's an oil. So corn oil, canola oil, olive oil, peanut oil, all these things are oils. They are liquid triglycerides. Butter and animal fat and lard are all fats. They're solid at room temperature, but they're all made up the same way. They all have the same structure. We have three large molecules known as fatty acids tied up to a glycerol molecule. The fatty acids are chains of carbon and hydrogen, about 20 carbon atoms long, bound covalently to hydrogen atoms with what we call an acid group at the end of the chain. The acid group is a term we use to describe, what makes it an acid. Well, acid groups always have the same type of structure. It's a carbon atom with an oxygen attached by a double bond with an OH group attached to the other side of the carbon. So that's an acid. If you have what we call it's a carboxyl group. I don't want to go into organic chemistry. When that's attached to a chain, it makes it an acid. Okay. So you have three of these long chains attached to glycerol. Glycerol is a 3-carbon alcohol. 3-carbon alcohol. We know it's an alcohol because the ending, OL, the suffix OL, glycerol, that indicates an alcohol, just like ethanol. The OL there makes it an alcohol. Propanol, is an alcohol. It's based on a number. In this case, the alcohol is based on the number of carbon atoms it has, but the ending is still OL. So glycerol is a 3-carbon alcohol, and it has these fatty acid chains attached to it. The main purpose of lipids is to store energy, because the lipids can be parked in the muscle, they can be parked within the cell, they can be parked in the liver, they can be parked in adipose tissue. Adipose cells are not, they're not fat. Adipose cells are just the storage area for fat. Adipose cells can enlarge or shrink based on the amount of fat that they're storing. And so that's where we store this energy. We can draw on this energy later on when we need it. Insulation, we have a layer of fat in our hypodermis. The third layer down in our skin, we have the epidermis, the dermis, and the hypodermis. So we start seeing layers of adipose cells with fat stored in there. That's to keep us warm in cold temperatures and cool in hot temperatures. But it's there to insulate us. And it's there those layers are there to protect us. Many of our organs have no protection in the viscera except a layer of fat. Our kidneys, for example, are suspended high up in the back of the abdominal cavity, just below the diaphragm. We say they are retroperitoneal, meaning they're in the back wall of the abdominal cavity. The only protection they have is they are embedded in a thick layer of fat. That's all they've got. So we use this fat as protection. So this is what your triglyceride looks like. All triglycerides look like this. There's your glycerol over here, your 3-carbon alcohol. It is this OH group that makes it an alcohol. And over here, your fatty acid chains here, long chains of carbon and hydrogen, usually no more than 20 carbons in a row, and it has all the hydrogens attached to it. This is the alcohol group. The acid group right here, the carbon with a double bonded oxygen and an OH group attached to it. So that OH is called hydroxyl. And as we used to say in organic chemistry, well, that's the C double bond OOH. Just got used to saying it that way. All you got to remember is that's the acid group that makes that an acid chain. So we call them, these are the fatty acid chains. Here are the fatty acids. So 20 carbon atoms linked together with all their hydrogens filled up, and an acid group in the end is a fatty acid. And we have 3 of these. You remember, these are triglycerides. Tri means 3. So we have 3 fatty acid chains covalently bound to the glycerol. And it looks like this over here. There's the glycerol, there's the fatty acid chain 1, 2, and 3. Now, a triglyceride can be made up of saturated fats or unsaturated fats. Saturated fats. Well, saturated fats are all held together by covalent bonds. Covalent bonds here mean that, well, we know what a covalent bond is, but it's a single covalent bond. A saturated fat, a saturated fatty acid, has every available space that can hold a hydrogen. Holding onto a hydrogen, it contains its maximum number of hydrogen atoms. So we have single bonds everywhere. So it looks, all these are single bonds, single covalent bonds. So that carbon can hold 2 hydrogens. That carbon can hold 2 hydrogens. That carbon can hold 2 hydrogens. This one in the end can hold 3 hydrogens. Same here. Each one can hold, if you're in the middle of the chain, you can hold 2. If you're on the end, you can hold 3. But every available space that can hold a hydrogen has a hydrogen there. There are no double bonds between the carbons to interfere with the ability to hold the hydrogens. A saturated fat is generally solid at room temperature. Butter is a saturated fat. It's solid at room temperature. Animal fat like that you would trim off of a piece of meat, is a saturated fat. Lard, rendered fat that you use for baking. The best bakeries in the world would probably use lard in lieu of Crisco because it does a better job. So as a shortening, so these are all solid fats, all made up of saturated fatty acids. Saturated fatty acids have their hydrogen chains all filled up with the largest number of hydrogens they can hold. Every carbon will bind to 2 hydrogens, except the one in the end will bind to 3. There are no double bonds in here anywhere. This is what a saturated fatty acid chain looks like. Carbon, 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 and so on. Hydrogens all the way down here until you get to the end. And there's the 3 carbons and the 3 hydrogens here. Everything else is 2 hydrogens. And of course, there's the acid group at the end down here. The opposite of this is the unsaturated fatty acid. Unsaturated fatty acids are different. They have at least 1 double bond in there between the carbons. And as such, they don't have the maximum number of hydrogens. Here we have a double bond between this carbon and this carbon. You can see that no hydrogen here and no hydrogen here because the electrons that would normally be shared with the hydrogens are now being shared by these 2 carbons. What happens is that the unsaturated fatty acid, we call it unsaturated because it doesn't have the maximum number of hydrogens in there. The unsaturated fatty acid will bend at the double bond. It will bend and kink and twist and move around. It's often been described as pinwheels around the double bond. And what this does is it prevents something occurring called van der Waals attraction. Remember van der Waals? Van der Waals is 1/100th of the strength of a hydrogen bond. Van der Waals occurs when there is unequal sharing of electrons in a covalent bond. Now, polar bonding has unequal sharing of electrons all the time. You know, polar bonds have positive and negative ends. Fats don't have positive and negative ends. But what will happen randomly is as electrons are spinning around their hydrogens and around their carbons, they will randomly stretch their orbits and then stretch back, and they will appear on one side of the molecule more frequently than the other. And this makes one side of the molecule slightly more negative and the other side slightly more positive. And if you have a long chain of fatty acids linked together, like we have back right here, if we have this long chain of fatty acids, if we have a slight unequal sharing of electrons here and here, we now have positive and negative charges that they are transitory. They're not permanent. They come and they go, they come and they go. But when they come, they attract the positive side of one molecule to the negative side of another molecule. That's van der Waals attraction. So they're magnetically attracted briefly. But these chains are so long, 20 carbons long, that it's an ongoing thing. So what will happen is that the fatty acid chains will stick together. So if you are a saturated fat, your chains will stick together, and that makes you a solid at room temperature. The fact van der Waals attraction is pulling you in. Van der Waals attraction is what makes butter solid at room temperature. It's what makes animal fat solid at room temperature. It's what makes lard solid at room temperature. Because a slight attraction. It isn't much of an attraction. It's 1/100th the strength of a hydrogen bond, but it's enough to pull the molecules together. And they don't stay together. Well, they do, but it's not because it's the same set of electrons. It's this random motion of electrons all up and down the chain over and over. You remember, they're moving at the speed of light, 186,000 miles per second. I can't wrap my head around something moving that fast, but they're doing it over and over and over again. They appear solid because they are solid. And so thanks to van der Waals attraction, an unsaturated fat is solid. But if there is a kink in the chain, then they're unsaturated. First of all, they're unsaturated because there aren't enough hydrogens there to fill up all the spaces. Second of all, the kink in the chain causes the fatty acid to bend and twist there at that kink, maybe even pivot around the kink. And that prevents van der Waals from occurring. So you can't get that attraction of the positive and negative sides when one of the chains is bent out of position. And so now you end up with a liquid fat. It's still a triglyceride, but it's a liquid fat because there is no van der Waals attraction going on. Okay, so I said anywhere up to 20 carbons is the length of the chain. You may, if it's unsaturated, then you have a kink. If it's saturated, you have every available hydrogen you can possibly have. The maximum number of hydrogens will be in that chain. And of course, they'll get van der Waals attraction, and the chains will stick together, and you have a solid. Now, an unsaturated fat has at least a double bond. It's also shy 2 electrons and 2 hydrogens. An unsaturated fatty acid has 1 double bond. A polyunsaturated, a term you've probably heard, particularly in cooking or advertising. If you're like me and because I'm a geek, I walk through and when we go to Food City, I spend time reading the labels bottles of oil to see which one's the best. I'll tell you that they're all pretty much about the same as far as the makeup of calories and stuff like that, saturated fats and unsaturated fats. My wife likes olive oil, so we get olive oil. That makes it real simple. Anyway, unsaturated fatty acids have one double bond. Polyunsaturated fatty acids have two or more double bonds, so they can have a kink in two places. And so on the label, since we can see what percent of it is polyunsaturated, we can see what percent is monounsaturated. Saturated fats, usually a straight chain held together by van der Waals attraction, saturated, all the hydrogens that can possibly be there are there. Unsaturated fats have a bend in it. They have a kink, like down here. We see it in the bottom right corner. We see it up here with oleic acid with a kink right there, as opposed to a saturated straight chain lining up there. So saturated fats are held together by van der Waals attraction. They're going to be the solid fats, lard, animal fat, butter. Those are going to be saturated fats, van der Waals attraction. Unsaturated fats are all the plant oils. The plant fats. Plant fats are not held together by van der Waals. The plant fats are unsaturated. They have at least one double bond in there, usually more. Usually they're polyunsaturated. So those are all the oils, the olive oil, the corn oils, things like that. So again, unsaturated fats have unsaturated fats are going to have fewer hydrogens. They're going to have a kink in the chain. They're going to be liquid at room temperature. Trans fats. Term here, trans and cis fats. Trans fats are unhealthy. See, oils also tend, in chemistry, molecules all tend to twist and bend in one direction or the other. Glucose, the carbon and hydrogens in there tend to be in one side or the other of the molecule. Do they bend to the right or they bend to the left? And depending on which side of the molecule you're looking at, or which side of the molecule a carbon and a hydrogen are on, will determine the properties of the molecule. So, the sides we refer to are cis and trans. A trans fat has its hydrogens and carbons turned in one direction. Most fats are called the cis fats, and their carbons and hydrogens are turned in the other direction. When you modify a normal healthy fat and you force the carbon and the hydrogen to occur on the opposite side of the molecule, we call it a trans fat. This is a modified oil, and they have a trans fat offers some great properties as far as stability and packaging and flavor enhancement and stuff like that in food, but it also creates some unhealthy conditions inside the body. Normally, oils are designed to, oils are fairly healthy for us. Oils are designed to have their carbons and hydrogens turned in on one side. Don't ask me, why they're that way. It's just the way they're designed. Oils are healthier than the animal fats. But if we alter the shape of the structure of the fat, then we run into some conditions. Now, what are some of the really healthy oils? There's this term called omega-3 fatty acids, oils from different sources. are very, very healthy for us, are considered the low cholesterol producing oils, like like fish oils, certain types of fish oils. And yes, it's from an animal, but it's a fish oil, and that tends to have help to lower our cholesterol levels. Now, I'll explain more about that here in a second. So let's take a look at this.
Butter, lard, margarine, and solid oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids are interacting.
We know that fatty acids are a great source of stored energy. That's what they do. That is the great benefit here from fats, is they hold 10 calories per gram of stored energy, and that's a good thing. And so we store fats in our bodies as an energy source. It's an energy reserve. All those carbons and hydrogens, and they're bound together, have all those covalent bonds with all those electrons in the valence shell with all that potential energy. That's a lot of stored energy right there. So now, where we see some changes in the shape of the molecule, as I said earlier, are where we have the, if they're unsaturated, right here, oleic acid, one double bond right there. It will kink and bend and twist at that double bond. And so we won't have that, there'll be no van der Waals attraction. There'll be no sticking together. It doesn't affect the amount of energy it can hold. I mean, it's only losing 2 electrons. It's only losing 2 hydrogens. The electrons are still there. The electrons are now shared between the carbons. Remember, it's a double bond, so it's using, instead of sharing 2 electrons, it's sharing 4 electrons. So we didn't lose the electrons. We just don't have the hydrogens. And the potential energy is in the electrons, are in the electrons, is in the electrons. So we can have an unsaturated fatty acid, still full of energy, or what we call linoleic acid, which is polyunsaturated, a double bond here and a double bond here. Again, we haven't lost the electrons. We are now sharing 2 sets of electrons here and here. There is a process, though, in food chemistry that you can break the double bonds in an unsaturated fat and force hydrogens onto those carbons that didn't have them. It's known as hydrogenation. Clever name for that, hydrogenation. When you do that to a oil, when you hydrogenate an oil, it becomes a solid. If you hydrogenate, if you break the double bonds in an oil and hydrogenate the oil, add hydrogens to the carbons that didn't have all their hydrogens, now the oil will become a solid. That's how margarine, a butter substitute. That's all margarine is. It's a butter substitute. It was developed probably 100 years ago as a butter substitute. You add hydrogens to the oil, to a corn oil, it turns solid. And if you want to take a look at that, look at margarine in the store, look at Crisco shortening. Crisco is based off of various vegetable oils, corn oil, or a mixture of vegetable oils. And you add hydrogens, you break the double bonds in the oils, add hydrogens to it, and lo and behold, we get a shortening that we use. In baking, it is a solid. It comes out as a white solid. That's what it looks like. It isn't white because it's made to look clean and pure. It's white because that's what happens when you hydrogenate oils. They turn white. The problem that occurs here is that when you hydrogenate these fatty acids, you may end up creating the trans fats. Trans fats form, they make the substance solid at lower temperatures than they do in their cis version. Their cis version is an oil, but their trans version is a solid. And we use that in the food industry. Trans fats have been used in the past to make stuff creamier, to improve its shelf life. How long is it going to sit on the shelf at your house or in the store? And what about the flavor? It's going to help stabilize the flavor, because when something has been hydrogenated, it has no flavor. But when you add flavoring additives to it, the natural flavoring is an artificial flavoring. So when you add that to something that's been hydrogenated, they last longer in the food. So an oil can be hydrogenated to form margarine, and we have a whole slew of different margarines that you can choose from, but you have to add coloring agents and flavoring agents and salt to it to get it to taste like, almost sort of like butter. And so we hydrogenate these foods. Now, there is a problem with this. When as I said, these oils don't appear, they only look like this in the bag. This is like 100. Oh, sorry. They look like what margarine does in the bag. This is like from 100 years ago, probably somewhere between the First and Second World War. Oils were in short supply. Butter was in short supply, and so the food industry started developing margarine. Margarine was sold without the flavor and without the color in there. You actually had to break open these little pellets inside the food and knead it, roll it together and knead it inside this bag, and then refrigerate it to get your margarine, so it would look and taste like butter. Even today, margarine, all these are margarine. There's Country Crock. I can't believe it's not butter. Even Land O'Lakes, and of course, I think that Shed Spread there, but I'm not certain. All these are, very, very common and frequently used margarines. But to get them to look and taste like butter, you have to add a lot of food additives in there, a lot of coloring agents, a lot of stabilizers, salt, going to have a lot of salt added to it, and various flavoring agents, I think flavoring colors. So even though you're not doing it by hand anymore, it's still in there. So that's the downside of using margarine. You're trading off less calories for the chemical additives that go in there. So what happens here with this? Well, trans fats, are they a good thing or a bad thing? Usually, most foods now that have been modified have no trans fats. They have been removed in the processing of this, because trans fats turn out to be not such a healthy item for us. When we hydrogenate oils, the trans fats may get formed, if we do it, artificially. Now, some trans fats get made naturally in the production of milk and in meats and things like that. I'll get back to that in a second. Trans fats, when you consume trans fats, it raises the level of what we call the low density lipoproteins, the so-called bad cholesterol. The Ldls, the bad cholesterol, levels increase in our blood. Now, what do the Ldls do? Well, cholesterol is an important component of our cell membranes and an important molecule used in the production of numerous steroid-based hormones. So we have to have cholesterol. A person that says, I'm never going to eat cholesterol again because it's dangerous, it's a bad molecule. And to be fair to cholesterol, over the past 50 or 60 years, cholesterol levels cholesterol has been described in the media as being horrible and a killer, and will lead to all sorts of diseases. And then it has said, oh, well, it's not so bad after all. And then it's back, again, we go back and forth on whether or not to eat eggs. The conventional wisdom says eat eggs. No, don't eat eggs. Eat eggs, don't eat eggs, because the yolk of the egg is full of cholesterol. So it's it's like coffee. Every year, studies come out and prove that coffee convincingly proves that coffee kills you. And then another study comes out and says, well, coffee's good for you. So it's like it goes back and forth, almost like whether, when to wear a mask or not wear a mask. But I'm not going to go into that. What happens here is that trans fats increase the production of what are known as the low density lipoproteins. Low density lipoproteins are used by the body to transfer cholesterol from the liver to various structures in the body. Now, everything we eat, what's it doing in the liver? Well, everything we eat is absorbed in the small intestine. Everything we eat and drink is absorbed in the small intestine first. After it's digested, it's absorbed in the small intestine and is transported immediately to the liver for what we call detoxification, to clean it up. Everything goes through the liver. So the cholesterol and the trans fats that we have taken in go into the liver. Now, the liver also stores cholesterol. Our cells need a certain amount of cholesterol. The low density lipoproteins that are produced in large quantities take vast amounts of cholesterol to the cells, including the cells lining the coronary arteries and the arteries in the brain and in the muscle of the heart. And so we start seeing an accumulation of cholesterol in these arteries. We call it plaque. It narrows the arteries. And there's a condition known as atherosclerosis, or commonly called heart disease, or what our grandparents would have called hardening of the arteries. Well, technically the arteries don't harden, they do get blocked. And the LDLs are taking large amounts of cholesterol to the cells. And so you have a greater risk of heart disease, having a heart attack, having a stroke, a clot blocking blood flow, sudden death, thanks to the accumulation of cholesterol. Now, why? So this is why we don't have trans fats. Trans fats are not allowed in processed foods. Now, what about animal fat, dairy and beef? Well, they have naturally occurring trans fats, and a person who maintains a diet that's high in animal fats, a lot of dairy products, a lot of meat products, particularly beef, and pork. Of course, pork is lighter, a little bit lighter in fat than beef, but animal products are going to be high in fat and high in LDLs. And so a person who has a diet, high in animal product, animal meat, animal fat, dairy products is going to be at a greater risk because of the presence of the trans fats that have occurred naturally. So that's why we are advised to moderate our eating to eat healthy. We can't just have meat and potatoes every night. When that was the that meat and potatoes was the stock dinner, the standard dinner for several generations of Americans for years and years. You know, it was always meat and potatoes with you know, some sort of dairy product thrown in on top of it. Meat and potatoes is a glass of milk. That's what generations of Americans ate, and generations of Americans developed heart disease at an astonishing rate. And we see heart disease levels have stabilized because people are trying, you know, at least part of the population is trying to eat healthier. Now, so we now know what trans fats do. We know that they stimulate LDLs to carry blood, carry cholesterol to the tissues. The HDLs, the good cholesterol, bring excess cholesterol back to the liver for destruction and removal. So we'd like to see the HDLs, the high density lipoproteins. They collect cholesterol, excess cholesterol at the cells, you know, lining the arteries, in the muscle cells and the brain. They collect that excess cholesterol and bring it back to the liver for destruction. That's what the liver does. The liver cleans up our blood. That's what it takes out all these different chemicals that are present in our food. It detoxifies things. It takes excess cholesterol. It will store some of it and it will destroy the rest. So our bodies can deal with cholesterol to a point. Cholesterol is not a bad molecule. We need a certain amount of cholesterol. If your patient says, I'm never eating cholesterol again, you need to explain to them why that is a foolish move. You know, because cholesterol levels, you know, we do need a certain amount of it. And if we don't get it, we're going to make it on our own. So we still have to, you know, pick up some of that in our diet. So LDLs versus HDLs. The you may have heard, I've probably said heart healthy in here. You may have seen commercials on TV advertising the benefit of Cheerios for a heart healthy diet. That's a true statement. Cheerios is a heart healthy food. It's made of oat bran, you know, because oat bran is the oat kernel surrounded by the outer husk, the bran, just like in wheat bran. Wheat is the kernel and the wheat bran surrounded. If you eat whole wheat, you're getting the bran too. The bran is not digestible. It causes wheat bran causes fiber, it produces fiber. It's made out of cellulose. In the oat kernel, the bran around the oat grain stimulates the production of HDLs, high density lipoproteins, the stuff that removes the cholesterol from our vessels. And so a person that eats Cheerios is going to increase their production of HDLs and improve the overall health of their heart and blood vessels. But so will any other cereal that has oat bran in it. You know, generic Cheerios, the knockoff brands, and the stuff that you find at Walmart in the jumbo bags in the bottom shelf, you know, whatever they're called, you know, or the store brand version of Cheerios, whether it's Food City or Kroger's or Walmart's, you know, oat circles, whatever, you know, they're called. Oatmeal has oat bran in it. It's heart healthy too. Anything with the oat bran involved here, and it usually shows up in the oat kernel, with the oat kernel all the time, is going to be heart healthy. And, you know, yes, so it's a valid statement that Cheerios does this, but so does every other oat-based cereal. Now, and unfortunately, oatmeal raisin cookies don't count, you know, despite the fact it does have oatmeal inside or oat bran inside. And it says, oh, it's got fruit and it's got raisins. It's not quite, you know, an oatmeal raisin cookie gives you the illusion of eating something healthy. Anyway, so, but we're, you know, the whole benefit there, you know, that's a true statement, what Cheerios says. What they're not saying is that everybody else that uses oat bran in their products is producing a healthier product too. So, okay. Right way here now. Okay. So what is the benefit of fat? Well, the triglycerides can get stored in our adipose cells. Remember, adipose cells have nothing to do with, weight gain. Adipose cells are all about storing fat. That's what they do. They're, adipose cells will shrink or enlarge based on the amount of excess fat that's left over, after processing it through the digestive system. See, what will happen is if you eat a diet that's high in carbohydrate, maintain a high carbohydrate diet, the carbohydrates are converted to glucose, and glucose shows up in your blood as blood sugar, and your body's tells the pancreas, hey, our blood sugar is up, let's take some into the cells. And we release insulin. Insulin allows the cells to open up and let the glucose come inside. And the cells take in as much glucose as they can process. They use some of it directly for energy. Some of it they're going to store in the form of glycogen. Particularly muscle cells store some of that glucose in the form of glycogen. Long chains of glucose is linked together. If they can't store any more, they'll store it in the liver as glycogen. And if there's even more glucose, they will string that together and form fats. They'll convert the glucose to fats and store it in the adipose cells. And we call this lipogenesis. Genesis is creation, the creation of lipids. And this is what's happening here. We have the creation of lipids. And so lipogenesis, creation of lipids. Excess carbohydrates can be converted into fats. And through lipogenesis. So maintaining a high carbohydrate diet can lead to significant weight gain from the fat cell, the adipose cells being filled up with lipids. Case in point, I had a friend of mine years ago that used to work for the State Department, and she had a posting in Paris, France, and really good, posting at the embassy. Well, every day they would leave the embassy. She and a bunch of her, and a large group of friends would leave the embassy at lunchtime or coffee break, whatever, and go to the nearest bakery. Imagine there's a bakery in Paris, and they would eat rolls and breads with butter. That was their coffee break, their donut break. They didn't have donuts; they had fresh breads and rolls of all kinds, and, fresh butter. Well, after a course of a year of that, she had gained 40 pounds. She had a 40-pound weight gain just by eating breads. All breads, of course, are starches, and the starches were converted to glucose, and the excess glucose ended up as fat. And it took her about a year to get that extra 40 pounds off, simply by eating all these breads. So starches are the starches are. You're going to have to tell him to go to where it is. I think it's back of the text. So, okay. So the starches are the starches are going to be excess starches are going to be converted. Excess starches are going to be converted to fats, and this is called lipogenesis. Now, necessary when we need those carbohydrates, we can break them down. I need to pause here just for 1 second. I'll be right back. Okay, sorry, I had the fence guy showed up early today. Apparently somebody had driven their lawnmower into their industrial lawnmower into the side of our fence and tore a hunk out of it. And we have to get an estimate on repairing the fence because we have dogs. And the fence guy showed up early, so I apologize for that. Let me get back here to where I was on. Okay, lipolysis. Anytime you see lysis at the end of a word, or just lysis by itself, it means cell rupturing. And so when we need nutrients, when we need glucose. We can rupture the glycogen molecules or the fat molecules. In this case, it's rupturing the fat molecules, the lipids, and release the fat, break it down, and form glucose. And that's what lipolysis means. Glycolysis is the breakdown of glycogen. Lipolysis is the breakdown of fat. Phospholipids look like this. They have a head and two tails. The two tails are the fatty acid chains. They substitute in phosphorus for the third fatty acid in the molecule, and they take a triglyceride and they substitute phosphorus in for one of the three chains. Two of the chains, leftover chains, become the tails, and the phosphate is the head, and they array these molecules in a double layer around the cell membranes, and the double layer has the heads facing out and the tails facing in. And this is how every membrane of every structure in our cells are made this way, with this phospholipid bilayer. And we'll talk a lot about that. Well, not a lot about it. We'll talk about it when we get into chapter 3 on cells. The steroids are the third category. This is what cholesterol looks like. It's a 4-ring structure with different functional groups attached to it. It has, we see cholesterol itself, vitamin D that we use for building bones. The steroid hormones, the sex hormones, for example, estrogen and testosterone, and the bile salts. The bile salts, bile is produced in the liver, stored in the gallbladder, and is used to digest fats. And so cholesterol is the basis for all of these molecules. You know, it's all derived from the cholesterol. They all look very similar. We also have cholesterol embedded in the cell membrane, sort of like rebar in concrete, to reinforce the strength of the cell membrane. And here are those icosanoids I mentioned earlier. The icosanoids are the lipids that act like hormones. They are, the most important of these are what we call the prostaglandins, and the prostaglandins help to regulate the inflammatory response. I mentioned that earlier. We want inflammation. We only want it in the areas where we need it. Like when you have a cut or a scratch, you have a red area, a red ring, if you will, around the cut or the scratch. And this red ring doesn't expand. It isn't a huge area of inflammation. It's just to promote healing and recovery at the site of the injury. And this is, you know, mitigated. It's controlled by the presence of these prostaglandins, which fall into this category of icosanoids. Okay, so that's 2 of the organic molecule categories. The third category are the proteins. We have lots of proteins. 30% of our cell mass is protein. Proteins do everything for us. We can even break down proteins for energy if we need to. Yeah, but we've already burned through the carbohydrates and the fats before we start breaking down the proteins. Proteins form both fibrous, meaning structural molecules, and globular, meaning reacting molecules like hormones. Your proteins all contain carbon, hydrogen, and oxygen, but now we see the presence of nitrogen. Nitrogen and hydrogen form ammonia, and ammonia is used in lots of cells. Here it's used in proteins as what we call the amino acid. Amino acids are nitrogen and 2 hydrogens linked together to an acid group and some functional group. And proteins are made up of amino acids, and they're held together by what are called peptide bonds. There are only 20 amino acids in our bodies, and yet we can make a wide variety of proteins, many amino acids in length. You know, for example, hemoglobin is 360 amino acids in length. The frequency of occurrence, the frequency of occurrence of amino acids in a protein and the types of amino acids that occur in the protein are dictated by our DNA. So while we only have 20 amino acids, we can produce a protein of any length. I mean, if you consider that there are only 26 words, 26 letters in the alphabet, yet a dictionary would have typically 300,000 words or more. So we can assemble these 20 amino acids into any combination we want. Every amino acid has two groups that are identical. It has the acid group on one side of the molecule and the amine group on the other side. And so it's the functional group in the middle that determines what the amino acid is going to do. We call it the R group. So your typical amino acid looks like this. There's the acid group on this side, or the carboxyl group. You know, there's this double bond to the oxygen, and then the oxygen and the hydrogen, the hydroxyl here. This is the acid side. This is the amino side. Ammonia and nitrogen and 2 hydrogens give you the amino group. Nitrogen and 4 hydrogens is ammonia. So when proteins break down, they tend to form ammonia. They tend to form what we call the nitrogenous wastes. But it is this side chain here, whereas the R on it, that's the functional group. That determines what the amino acid is going to be. The amino group and the acid group are the same in all 20 of them, but it's that functional group that determines what the amino acid is going to do. And many of them are very similar in structure, but totally different in what they trigger. So it is the functional group. Yeah. And so the sequence of amino acids dictated by our DNA is going to dictated by the order of them are dictated by our DNA, and we are going to see them show up in a very specific order in our proteins. I mean, consider hemoglobin. Hemoglobin is a protein that is 360 amino acids in length, spelled out very carefully in our DNA. However, we know that the number 6 amino acid in hemoglobin is called glutamic acid. However, that's where the however comes in. If instead of glutamic acid, we put in the valine, we put in the amino acid valine, that entire chain is wrong. Now that 360 amino acid chain is now defective. It is sickle. It's what's known as sickle cell hemoglobin. One mistake early on in the chain, and the structure between glutamic acid and valine is very similar. In fact, the instructions in the DNA are very similar. But one little mistake, taking glutamic acid out and valine in, makes a world of difference. Now, peptide bonds are what holds these amino acids together. They are links between the amino acids. The properties of the amino acids don't change. The properties of the amino acids, individual amino acids, they still have their functional groups. They are now held together by these peptide bonds. Sometimes we call proteins polypeptides, since the monomer of the protein is the amino acid. But you can see, we join them together. There's its functional group there and there, and so we still have the acid, we still have the amino group in here. So if you are a protein, you occur in one of four structures. You can be primary, which essentially is how the protein is coming out of the assembly site inside the cell, and the cell's making the protein. This is how it's chugging out of the assembly site. One after another, after another, after another. It's essentially in a straight line, linear sequence, if you will. Proteins never occur like that naturally. When they get made, they have to immediately be twisted. They have to be manipulated into their specific shape, because all proteins have unique shapes. The secondary shape is how, so we take this straight chain and we start twisting it and bending it into its secondary shape. Within the protein molecule, we can have what's known as the alpha helix or the beta pleated sheet shape. An alpha helix looks like a spring. We find that when we want to have resiliency, we want to have elasticity, we want to be able to rebound, so we see that in our different proteins, like our hair. Our hair is made up of alpha helix protein, because no matter what our hair looks like when we get up in the morning, we can brush it or comb it or even just push it over into whatever shape it's supposed to stay in. It returns to its normal shape thanks to this alpha helix structure in here, this coiled structure. The pleated sheets give us great strength. The tendons and ligaments that hold our muscles to our bones are made of collagen fibers. Collagen protein is arrayed like these pleated sheets where they're woven side by side by side. These individual strands of collagen are stronger than steel of the same size. And so they give great strength to the tendons that hold muscles to bones. Tendons are so powerful that they will usually snap bone before they themselves break. Now, the tertiary structure is what happens when you have a long chain of protein assembled with both the alpha helix and the pleated sheet structure woven in among itself. The tertiary structure is formed by hydrogen bonds that occur between the various parts of the molecule. And that's what twists it into its secondary structures. And then the quaternary is simply the assembly of several tertiary structures together, like hemoglobin is always the classic example of a quaternary protein. Hemoglobin has four sides to it. It's a four-part protein, and it's designed to have iron in the middle of the hemoglobin molecule and carry four separate oxygens. And this is what our primary structure looks like here. There's our alpha helix shape there, is sort of a spiral shape. The pleated sheet is like an accordion type, folder or whatever, where you have layers upon layers, but you can see the strength is drawn from the fact that they're all close together. A tertiary structure is a combination of both of these alpha helix and the pleated sheet, and a quaternary is a combination of two or more, usually four tertiary structures. And we have time to watch this.
Most proteins are folded into a complex globular shape. Each protein molecule consists of one of these.
We just went through the four levels here, but this is the primary structure here, but it's bending now and twisting around. Hydrogen bonds are forming here and here and here and here, drawing this into its alpha helix shape or into its pleated sheet shape, or both, to give it its final version. Many of these protein molecules fit on a cell as similar in an arrangement similar to a key going into a lock. So the shape of the protein molecule has to fit the receptor site on the cell, much like a key into a lock. If it doesn't fit, it's not going to work. So, okay. Okay, and this is a good place to stop. I apologize for that little interruption there. So I will see some of you the rest of the day in lab today or tomorrow, and we will definitely finish up this chapter, the chapter that never ends. We will finish this chapter up on Monday. So, anybody have any questions on anything before I get us out of here? Okay, then I will see you all later.